Hey everyone, tonight we're going to dive into something that's happening right now as we speak, and the scale of it is staggering. Species are disappearing from Earth at a rate that's over 1,000 times faster than anything in the natural world. We're talking about extinction rates that match the most catastrophic events in planetary history, the kind that show up in the fossil record as sharp black lines where entire worlds of life just end. The last time life vanished this quickly, it was 66 million years ago, when an asteroid 6 miles wide obliterated the dinosaurs. Before that, it was the Great Dying, the Permian extinction that wiped out 96% of everything alive in the oceans. But here's the thing, this time there's no asteroid, there's no supervolcano, there's no ice age. This time, we are the asteroid. And that's not hyperbole. When you look at the data, the collapse of insect populations, the emptying of the oceans, the atmospheric changes happening in real time, we're watching the early stages of Earth's 6th mass extinction unfold, not in some distant future, but now, in our lifetimes. And the patterns from every previous extinction tell us the same thing. Once these cascades begin, they don't slow down, they accelerate. So tonight we need to understand what that means, because the window for changing the trajectory of this story is measured in years, not centuries. This is one of those topics where the more you dig into the science, the more questions emerge, and I'd love to hear your thoughts as we go through this together. Make sure to subscribe if you want to explore more of these deep time stories that connect our past to our present, and drop a comment if you've noticed changes in your own area, because this isn't just happening in some abstract sense, it's happening in backyards and forests and oceans all around us. To understand what we're facing, we need to look back at Earth's greatest catastrophes. There have been 5 mass extinctions in the planet's 4.5 billion year history, and each one tells us something crucial about how life responds when the systems that support it begin to fail. The first happened 445 million years ago, during what geologists call the Ordovician-Silurian extinction. Back then, most life existed in warm, shallow seas teeming with strange creatures that look nothing like anything alive today. But the world was cooling rapidly. Massive ice sheets were forming at the South Pole, locking up so much water that sea levels dropped by hundreds of feet. Entire ocean basins emptied. The creatures that had thrived in those warm, shallow seas simply had nowhere to go. 85% of all species vanished. What's striking about this extinction is how it shows us that even gradual changes can trigger catastrophic collapses. The cooling didn't happen overnight. It unfolded over hundreds of thousands of years. But there came a point where the system couldn't adapt fast enough and everything unraveled. The second Great Dying came 70 million years later, during the late Devonian period. This one's particularly unsettling because it didn't happen all at once. Instead, it pulsed. Waves of extinction rolling across the planet over millions of years, each one claiming more species than the last. 75% of everything alive disappeared during these pulses. Scientists still debate what caused it, but the evidence points to ocean chemistry changes, possibly triggered by the evolution of deep-rooted plants that altered how nutrients flowed from land to sea. This pattern, extinction coming in waves, each worse than the last, is worth remembering, because that's exactly what we're seeing today in different ecosystems around the world. But the third extinction, the one that happened 252 million years ago, dwarfs everything else in Earth's history. The Permian Triassic extinction, scientists call it the Great Dying, erased 96% of marine species and 70% of land vertebrates. It came closer than any other event to sterilizing the planet entirely. The trigger was volcanism on a scale that's hard to imagine. The Siberian Traps, a region of volcanic activity covering an area larger than Europe, erupted continuously for nearly 1 million years. These weren't just ordinary volcanoes, they were flood basalts, pouring molten rock across vast landscapes while pumping massive quantities of carbon dioxide, sulfur compounds, and toxic gases into the atmosphere. Global temperatures surged by 18 degrees Fahrenheit. The oceans became acidic and filled with hydrogen sulfide, the same compound that gives rotten eggs their smell, except this was concentrated enough to poison the atmosphere when it bubbled up from the water. Vast dead zones spread across the seafloor. On land, the soil became too toxic to support plant life. Recovery took 10 million years. Think about that time span. 10 million years for life to rebuild even the basic ecosystems that could support diverse communities of species. And when it finally did recover, it was a fundamentally different world. The creatures that had dominated Earth before the Great Dying were gone forever. The fourth extinction, 201 million years ago, marked the end of the Triassic period. This one coincided with the breakup of Pangaea, the supercontinent that contained all of Earth's landmasses. As the continent split apart, massive volcanic eruptions once again flooded the atmosphere with greenhouse gases. 80% of species vanished, clearing the way for dinosaurs to become the dominant life forms on the planet. And then, of course, there's the extinction everyone knows, the one that ended the dinosaurs 66 million years ago. The Cretaceous-Paleogene extinction has captured our imagination because the cause is so dramatic and definitive. An asteroid 6 miles across slammed into what is now Mexico's Yucatan Peninsula with the force of billions of nuclear weapons. The impact vaporized the asteroid and a massive chunk of Earth's crust, launching debris into space that rained back down as molten glass. Wildfires swept across continents. A nuclear winter settled over the planet as dust and ash blocked out the sun. Most people don't realize that the asteroid wasn't the only thing happening. At the same time, massive volcanic eruptions in what is now India, Deccan Traps, were already stressing global ecosystems. While the asteroid impact may have been the final blow, our planet was already weakened. Here's the pattern we see in every mass extinction. It's never just one thing. Climate change triggers ocean chemistry changes. Habitat loss leads to food web collapse. Species disappear from the bottom of the food chain and effects cascade upward. Each stress makes organisms more vulnerable to the next shock. Which brings us to today. Right now, we're witnessing ocean acidification happening faster than it did during the Permian extinction. Atmospheric carbon dioxide levels are spiking more rapidly than during any previous mass extinction in Earth's history. Insect populations, foundation of most terrestrial food webs, are crashing at rates of 2.5% annually. Warning signs that preceded every previous mass extinction are flashing around us now, compressed into decades instead of millennia. Our question isn't whether we're in a sixth extinction. Evidence is overwhelming that we are. Instead, we need to ask whether we're already past the point where it can be stopped, or if we still have time to influence how severe it becomes. Every past mass extinction had tipping points, moments when cascading failures became unstoppable, when the planet's life support system shifted into a new, impoverished equilibrium. And those tipping points weren't gradual, they were sudden, irreversible, and they changed everything. In 1970, Earth had 4 billion people, and wildlife populations were relatively stable. Today we have 8 billion people and 70% of all wild vertebrates are gone. This isn't a prediction about what might happen. It's what already happened while we were building cities, raising families and going about our daily lives. Scientists track this through something called the Living Planet Index, which monitors populations of mammals, birds, fish, reptiles and amphibians around the world. Since 1970, just 53 years, these populations have declined by an average of 69%, but the global average masks some truly staggering regional collapses. In Latin America, wildlife populations have dropped by 94%. Nearly everything that was alive there in 1970 is now gone. Freshwater species have been hit the hardest, with an 83% decline globally. Rivers, lakes, and wetlands, the arteries of life on land, are being drained faster than species can adapt. But what makes this particularly alarming is that we're not just talking about rare or specialized creatures, we're watching the collapse of common species that have been abundant for millennia. Take insects, the invisible foundation that holds most terrestrial ecosystems together. In 2017, a study in Germany measured flying insect biomass in nature reserves and found it had declined by 75% in just 27 years. These weren't marginal habitats or polluted areas. These were protected reserves specifically managed for conservation. Puerto Rico's rainforests tell an even more dramatic story. Between 1976 and 2012, ground-dwelling insects declined by 98%. Canopy insects dropped by 80%. Scientists who had studied these forests for decades described returning to places that were once alive with the sounds of insects and finding them eerily silent. This matters because insects aren't just small creatures we barely notice. They pollinate the plants that produce about 1/3 of everything we eat. They decompose organic matter, cycling nutrients back into the soil. They feed the birds, the bats, the frogs, entire food webs built on foundations that are crumbling beneath our feet. Remember when road trips meant stopping every few hours to scrape bug splatter off your windshield? When did you last have to do that? Scientists call it the windshield phenomenon, and it's one of those everyday observations that reveals something profound about how much our world has changed. But insects are just the beginning. Our oceans, covering 70% of the planet's surface, are emptying at a rate that would have been unimaginable just decades ago. 90% of large fish, tuna, marlin, swordfish, sharks, have vanished since 1950. These are apex predators that have roamed the oceans for millions of years, and we've eliminated 9 out of every 10 in less than a human lifetime. Coral reefs, often called the rainforests of the sea, have lost 50% of their coverage since the 1980s. These aren't just pretty underwater landscapes, they're nurseries for about 25% of all marine species. When coral reefs die, everything that depends on them disappears too. Scientists studying the Great Barrier Reef, the largest living structure on Earth visible from space, have watched massive bleaching events become annual occurrences instead of rare disasters. Water temperatures that used to spike occasionally now stay elevated for months at a time. Corals that took centuries to grow die in weeks. Even the microscopic life in our oceans is disappearing. Phytoplankton, tiny marine plants that produce about 50% of the oxygen we breathe, have declined by 1% annually since 1950. That might sound small, but compounded over 70 years, we're talking about a massive reduction in the ocean's ability to sustain life. Meanwhile, dead zones in the ocean, areas where pollution has consumed all the oxygen, leaving water that can't support complex life, are doubling in size every decade. These aren't small pockets of damaged water. Some dead zones now cover areas larger than entire countries. What makes all of this particularly troubling is the speed. Natural background extinction, the rate at which species normally disappear, runs about 1 species per million per year. Right now, species are vanishing at least 1,000 times faster than that natural rate. For vertebrates specifically, we're looking at extinction rates about 100 times higher than normal. But even those numbers don't capture the full picture, because we're losing species faster than we can catalogue them. Scientists estimate that Earth hosts somewhere between 8 and 100 million species, but we've formally described fewer than 2 million. Every day, species we've never even discovered are disappearing forever. Consider what scientists call functional extinctions, species that still exist but in numbers too small to play their ecological role. Northern white rhinoceros, 2 females left, both elderly, both infertile. Vaquita porpoises in Mexico's Gulf of California. Fewer than 10 individuals remain. Chinese paddlefish, which survived for 200 million years through multiple mass extinctions, was declared extinct in 2020. These aren't just tragic losses, they're canaries in the coal mine, warning us about ecosystem-wide collapses that are already underway. When apex predators disappear, prey species can explode in numbers until they strip their habitat bare. When pollinators vanish, plant reproduction fails and forests begin dying back. When soil organisms are killed by pesticides, nutrient cycling breaks down and agricultural productivity plummets. Scientists have documented these cascading effects in ecosystems around the world. Remove wolves from Yellowstone, and deer populations explode, overgrazing vegetation until rivers change course. Lose sea otters along the Pacific coast, and sea urchin populations boom, creating underwater deserts where kelp forests once thrived. Watch vultures disappear from India due to pesticide poisoning, and rotting cattle carcasses create breeding grounds for disease that spreads to humans. Each extinction creates vulnerabilities that make the next collapse more likely. Each missing link in the food web puts additional stress on the survivors. And we're not just losing individual species, we're losing the intricate relationships between species that have evolved over millions of years. What's particularly unsettling about these collapses is how they're happening in plain sight, yet somehow remaining invisible to most of us. Psychologists call this shifting baseline syndrome. Each generation accepts the degraded state of the environment they grew up with as normal. Your grandparents might remember clouds of passenger pigeons darkening the sky, but you've never seen them, so their absence feels normal rather than tragic. Children today grow up in a world where finding a monarch butterfly is notable rather than routine. They don't know that streams once teemed with salamanders, that forests buzzed constantly with insects, that night skies were filled with the calls of migrating birds. What feels like abundance to them would have seemed like ecological disaster to someone living a century ago. This psychological disconnect is amplified by our increasingly urban lives. More than half of humanity now lives in cities, surrounded by concrete and glass instead of functioning ecosystems. We order food from apps instead of watching it grow. We get our nature from documentaries instead of daily experience. When David Attenborough shows us a thriving coral reef, we assume that's what reefs still look like everywhere, not realizing we're watching footage of one of the few healthy reefs left on the planet. Meanwhile, our media gives us a distorted sense of conservation success by focusing on individual rescue stories rather than system-wide collapse. We see headlines about a panda birth at the zoo or a successful sea turtle release, and these feel-good stories mask the broader reality that wildlife populations continue plummeting. It's like celebrating the rescue of passengers from the Titanic while ignoring that the ship is still sinking. But beyond our psychological blind spots, there are deeper patterns in what we're losing that reveal just how far this collapse has already progressed. Scientists use the term trophic cascade to describe what happens when species at one level of the food web disappear and the effects ripple through the entire system. Madagascar offers a stark example. Lemurs, the island's signature primates, are vanishing so rapidly that 96% of species are now threatened with extinction. But lemurs aren't just charismatic animals tourists come to see. They're seed dispersers, carrying fruits through the forest and depositing seeds in their droppings miles from the parent trees. As lemur populations crash, forest regeneration slows, then stops entirely. Trees that have relied on lemurs for millions of years begin aging out without replacement. Entire forest types are becoming evolutionary dead ends. Similar patterns are playing out in forest worldwide. Large mammals that once dispersed seeds across vast distances have largely disappeared. Elephants in Africa and Asia, tapirs in Central and South America, hornbills and cassowaries in Southeast Asia, these ecosystem engineers shape the very structure of their forests through their feeding and movement patterns. Without them, forests become fragmented islands of older trees with no mechanism for long-distance colonization. Even our agricultural systems, which we think of as separate from wild ecosystems, depend on services provided by wild species. Native bees, butterflies, and other pollinators are responsible for pollinating crops worth hundreds of billions of dollars annually. But pollinator populations are crashing globally. Some regions have lost 70% of their wild pollinators in just 2 decades. Commercial beekeepers are struggling with colony collapse disorder, where entire hives of honeybees simply disappear. Beekeepers who once expected to lose maybe 5% of their colonies each winter now routinely lose 30 to 40%. In some regions of China, apple orchards have already shifted to hand pollination because wild pollinators have vanished entirely and managed honeybee populations can't handle the workload. Soil itself, the foundation of terrestrial life, is disappearing at rates that should alarm anyone who eats food. We've lost 33% of the world's topsoil in the past 150 years, and it's being lost about 1,000 times faster than it forms naturally. But it's not just erosion. Industrial agriculture has fundamentally altered the soil microbiome, the billions of bacteria, fungi, and other organisms that make soil alive. Intensive pesticide use has created what some scientists call biological deserts in agricultural soils. The complex networks of mycorrhizal fungi that connect plant roots and help them share nutrients have been severed by chemicals designed to kill. Earthworms, which Darwin called nature's ploughs for their role in aerating soil and cycling nutrients, have disappeared from vast areas of farmland. At current rates of soil degradation, agricultural scientists estimate we have maybe 60 harvests left before widespread crop failures become inevitable. 60 harvests. That's about 60 years, assuming we don't accelerate the destruction. Your children or grandchildren could live to see global food systems collapse simply from running out of healthy soil to grow crops in. But perhaps most concerning is what's happening to the species we can't see. the microorganisms that form the base of most food webs and regulate the chemistry of our planet. Bacterial communities in the ocean that have remained stable for millions of years are shifting rapidly as waters warm and acidify. Ancient soil microbiomes that took millennia to develop are being wiped out by single applications of broad-spectrum herbicides. These microscopic ecosystems process the fundamental elements of life: carbon, nitrogen, phosphorus, cycling them between living organisms and the physical environment. When microbial communities collapse, these cycles break down. Nutrients become locked in forms that plants can't use. Waste products accumulate instead of being decomposed. The basic chemistry that supports complex life begins to fail. Scientists studying these microbial collapses describe them as invisible extinctions, losses that are absolutely critical but almost impossible for the general public to understand or care about. You can't make a documentary about charismatic bacteria. You can't put soil fungi in a zoo. But these invisible extinctions may be the most important ones happening. All of this is occurring against a backdrop of accelerating habitat destruction. Every year, an area of forest larger than Greece disappears. Wetlands, among the most productive ecosystems on Earth, are being drained 3 times faster than forests are being cut down. Grasslands, which once covered vast areas of every continent except Antarctica, have been converted to agriculture at even higher rates than forests. We're not just losing species, we're losing entire ecosystem types that took millions of years to develop. And once they're gone forever. Evolution doesn't run in reverse. Extinction is permanent. What makes this particularly tragic is that much of this destruction is happening for short-term economic gains that pale in comparison to the ecological services being lost. A hectare of intact Amazon rainforest provides ecosystem services worth thousands of dollars annually. Water regulation, carbon storage, climate moderation, biodiversity maintenance. But it gets cleared to create cattle pasture worth maybe a few $100s per year. We're strip mining the biosphere for temporary profit, destroying natural capital that took millions of years to accumulate. When people hear about past extinctions, the numbers sound unreal. 96% of marine species gone, or forests turning silent for millions of years. But it's easy to forget that none of those collapses began with silence. They began with triggers, small changes, often almost invisible at first, that multiplied into global transformations. And the unsettling thing is how familiar those triggers sound when compared to what's unfolding around us now. Take climate. At the end of the Permian period, the Siberian traps poured lava for centuries, releasing gases that raised global temperatures by roughly 5 degrees Celsius. That shift destabilized nearly every ecosystem on Earth. Today, our climate projections point toward 4 degrees of warming by the end of this century if we continue on our current path. 4 degrees might not sound like much. It's the difference between a mild afternoon and a hot one. But on a planetary scale, it separates an ice age from a greenhouse world. What makes this even stranger is the pace. When climates shifted in the deep past, species responded by migrating. Trees inched across continents, animals followed the shifting belts of vegetation, and oceans reshuffled their currents. Scientists now measure something called climate velocity, which is the speed at which a species must move to keep pace with changing conditions. Right now, that number is around 6 kilometers per year. A bird might be able to make that adjustment. A fish population might drift with changing water temperatures. But a forest of oaks or pines can only migrate at about 1 kilometer per year, maybe less. Mountains and coastlines become walls instead of corridors. In the Arctic, warming is happening 4 times faster than the global average, and there is no farther north for creatures to run. If temperature shifts set the stage, then ocean chemistry writes the next act. Over the last 250 years, since the beginning of the industrial era, the oceans have absorbed so much carbon dioxide that their acidity has increased by 30%. That's a drop in pH of about 1/10 of a unit, which sounds small until you realize that ocean chemistry is a delicate balance that took millions of years to stabilize. What's more troubling is that the current rate of acidification is estimated to be 10 times faster than during the Great Dying at the end of the Permian. In practical terms, it means shell-forming creatures like corals, oysters, and plankton are struggling to build the calcium carbonate structures that their lives depend on. In some regions, scientists have watched baby oysters dissolve before they can even form a shell. The ripple effects are enormous. Coral reefs, which nurture a quarter of all marine life, are bleaching and crumbling. Microscopic plankton, responsible for half of the oxygen we breathe, are declining at about 1% per year. In their place, we're seeing an ocean increasingly dominated by jellyfish and algae, organisms that thrive in chaos but do little to support the food webs we rely on. And then there's the methane. Locked away in permafrost and frozen hydrates on the seafloor are vast reserves of carbon, about 1,700 billion tonnes in the Arctic alone, more than double the amount currently in the atmosphere. As permafrost thaws, it's not just releasing carbon dioxide, it's releasing methane, a greenhouse gas more than 25 times as potent in the short term. Scientists describe a clathrate gun hypothesis, the fear that warming could destabilise methane hydrates on the seafloor, releasing them in a runaway pulse. We don't know how close we are to that kind of threshold, but what we do know is that atmospheric methane is already spiking beyond predictions, especially in the Arctic. It raises the unsettling question: what happens if the feedback loops that ended worlds in the past are now waking up on our watch? And feedbacks are everywhere once you start looking. The Amazon rainforest, once called the lungs of the planet, is showing signs of becoming a carbon source instead of a sink. Vast areas of permafrost are thawing not just gases but ancient pathogens, bacteria and viruses that have been frozen for tens of thousands of years. Ice loss reduces Earth's albedo, meaning less sunlight is reflected back into space. That in turn accelerates warming, which melts more ice. Fires in Australia, California and Siberia now generate their own weather systems. Thunderstorms born from flames, lightning bolts sparking new infernos. All of these shifts share a haunting rhythm with extinction events of the past. The triggers don't act alone. They reinforce one another, locking ecosystems into spirals that are difficult to slow and impossible to reverse. But the story isn't just in the air and water, it's also in the ground beneath our feet. In the last 150 years, we've lost about a third of the world's topsoil, much of it washed away by erosion or exhausted by intensive farming. Soil forms at rates roughly 1,000 times slower than it is disappearing. This means we're burning through a resource that should last millennia in the span of a few generations. Pesticides and fertilizers further disrupt the living communities within soil. Networks of fungi, bacteria and earthworms that Darwin once described as the architects of the natural world. Without them, nutrient cycles break down, crops fail, and the very base of terrestrial ecosystems falters. Some agricultural scientists warn we may have only 60 harvests left before widespread collapse of fertile soils. 60 harvests. That's not geologic time, it's human time. Fresh water adds another layer to the picture. Right now, 2 billion people lack reliable access to clean drinking water. Aquifers that took thousands of years to fill are being drained in decades. In many parts of the world, major rivers no longer reach the ocean during the dry season, their flow exhausted by dams, irrigation and drought. The Nile, the Colorado, the Indus, all names tied to the birth of civilizations, are now rivers that sometimes vanish before they complete their course. If water wars once sounded like science fiction, they're already beginning in localized conflicts across arid regions. And while nature provides most of the triggers, we've also engineered a few of our own. Our civilization runs on a network of more than 400 nuclear reactors, all of which depend on stable power and cooling. If social or climatic disruptions make those systems fail, reactors risk meltdown, scattering radioactive contamination into already fragile environments. On top of that, we still live with the nuclear arsenals of the Cold War, thousands of weapons that could, in a moment of conflict or miscalculation, unleash a different kind of extinction trigger. Even more subtle risks exist, like electromagnetic storms from the sun, or man-made pulses that could fry the infrastructure holding our complex world together. When you line these threads side by side, climate acceleration, collapsing oceans, thawing methane, failing soils, vanishing fresh water, and the shadow of nuclear risks, you start to notice a pattern. None of them exist in isolation. Each amplifies the others, each takes a strain already felt and multiplies it. And together, they create a landscape that feels eerily similar to the opening chapters of those ancient mass extinctions. The more you sit with these triggers, the more they stop looking like isolated problems and start feeling like instruments in a symphony. Not a symphony anyone would choose to hear, but one that history tells us plays whenever the Earth's systems are pushed beyond balance. What's unusual about our moment is not that the instruments are tuning up, it's how many are playing at once and how quickly the tempo is accelerating. Think again about the Permian extinction. Volcanic eruptions released greenhouse gases, which raised temperatures, which changed ocean chemistry, which triggered hydrogen sulfide release. That alone was enough to erase nearly all life in the sea. But compare that single volcanic driver to our present, and you see how broad the spectrum has become. Instead of one massive eruption, we are running 1,000 smaller engines, factories, vehicles, power plants that collectively rival the output of geologic cataclysms. We've taken the role once played by tectonic rifts and asteroid impacts and woven it into daily life. It makes you wonder, do we even notice when we cross thresholds anymore? A tipping point isn't always obvious in the moment. A glacier doesn't announce the exact day it stops growing and begins its retreat. A rainforest doesn't send out a signal when it turns from carbon sink to carbon source. Sometimes the change is visible only in hindsight, once the balance has already flipped. That is perhaps the most haunting aspect of studying past extinctions. They show us that systems often look resilient until suddenly they aren't. The Amazon is a case in point. For decades it absorbed more carbon dioxide than it released, helping to buffer the atmosphere. But in some regions, scientists now measure the opposite. Fires, deforestation, and drought have combined to flip the equation. Instead of absorbing carbon, those areas are bleeding it out. The rainforest still looks green and lush from a satellite image, but chemically it is beginning to play a different role in Earth's system. That shift may not be reversible once it spreads too far, or consider permafrost. For thousands of years it has acted like a freezer, locking away ancient carbon. But the freezer door is now ajar, and with every degree of warming it opens wider. What escapes is not only greenhouse gases but long-dormant microbes. We've already seen anthrax outbreaks in Siberia linked to thawing carcasses of animals buried in the ice. It raises eerie questions about what else waits in that frozen archive and how prepared we are to encounter it. Then there is the hidden arithmetic of water. Civilization has always followed rivers: Nile, Tigris, Indus, Yellow. They are more than flows of water, they are timelines of culture, but in a hotter world those rivers strain to carry both their ancient loads and the new demands we place upon them. The Colorado River, once a torrent carving canyons, now sometimes fails to reach the sea at all. The Indus, lifeline for hundreds of millions, depends on Himalayan glaciers that are retreating year by year. It is sobering to think that the very features that birthed civilization may not be reliable companions in its continuation. Soil tells a similar story. It doesn't vanish in a dramatic flash. It just grows thinner season by season, carried away by wind, washed into streams, exhausted by fertilizer. When people hear that we may have 60 harvests left, it sounds like a countdown clock. But the truth is more diffuse and unsettling. Soil loss doesn't strike evenly. It frays at the edges, leaving some regions barren while others still look healthy. That patchiness hides the severity, lulling us into thinking we have more time than we do, and yet civilizations have risen and fallen on much less. What is striking across all of these examples is the sense of compression. In the fossil record, an extinction can look like a single thin black band in the rock, but in reality it played out over tens of thousands, sometimes hundreds of thousands, of years. In human terms, that allowed generations to adapt, migrate, or at least bear witness to slow decline. Now the same scale of change is telescoped into decades. A single lifetime can hold the beginning, middle, and end of systems that once spanned epochs. And we are left with a paradox. On the one hand, we have never been more aware of these processes. Satellites measure the greening and browning of the Earth in real time. Ocean buoys record the chemistry of the seas. Climate models project futures on century-long scales. No past species ever had such foresight. On the other hand, foresight doesn't guarantee action. Knowing the trajectory doesn't always mean we step off it. In fact, it sometimes leaves us paralyzed, caught between awareness and denial, between the scale of the problem and the limits of our institutions to respond. It's worth pausing here to think about how civilizations in the past responded to environmental change. The Mayan cities collapsed in part from drought that lasted decades. The Akkadian Empire in Mesopotamia fell after a century-long dry spell. The ancestral Puebloans left their great cliff dwellings in the American Southwest as rainfall patterns shifted. In each case, people adapted as best they could, migrating, reorganizing, creating new ways of life. Yet none of them faced changes driven by global processes. Their challenges were regional, ours are planetary. This is why some scientists describe our moment not as a crisis of individual systems, but as a crisis of complexity. Every link in the chain depends on every other link working smoothly. Food depends on soil, water, and pollinators. Energy depends on stable supply chains and functioning grids. Health depends on ecosystems that filter water, regulate climate, and buffer disease. When one link snaps, it doesn't just disappear, it tugs on the others until more links strain and give way. The triggers we've discussed are dangerous not only for what they do individually, but for how they interconnect. And so we arrive at an unsettling reflection. If the 5 great extinctions of the past were each set off by 1 or 2 dominant triggers, volcanoes, ice, impacts, then what do we call a moment when half a dozen are acting together, each amplifying the others? Are we already living in the opening act of a new mass extinction? Or are we still standing in the narrow window where feedbacks can be slowed, where some cascades can be interrupted? The rock record cannot tell us, because no previous extinction was set in motion by a single species with the ability to see it happening. It's tempting to end this with a clean conclusion, some way of sorting the data into an answer. But maybe the better place to leave it is with the question itself. Because questions hold possibility, and possibility is what makes the difference between inevitability and choice. We may not stop every trigger from firing, but perhaps the point is to slow the chain reaction, to stretch out the timeline so more life has room to adapt. That is not the kind of hope that makes headlines. It is quieter, more like tending a fire through a long night, keeping embers alive so that warmth is still possible come morning. Looking back at the great extinctions, one thing is clear. The Earth always found a way to recover. Forests returned, oceans refilled, new species rose to take the place of those lost. What changed most radically was not life itself, but the cast of characters and the balance between them. In our time, the question becomes sharper. If the stage is shifting underfoot, what does that mean for us? A species that has filled nearly every corner of the world, tied together in a net of trade, technology, and fragile stability. Genetic evidence suggests that long before skyscrapers and satellites, our ancestors nearly disappeared. Around 74,000 years ago, the Toba supervolcano erupted in what is now Indonesia. Ash-covered skies, global temperatures fell, and the human population may have dropped to just a few thousand. It is humbling to think that every one of us alive today descends from that small remnant. Back then, survival meant stone tools, fire, and mobility. Communities were small, and knowledge was stored in memory and tradition. Somehow, that was enough to keep the flame alive. Now compare that to the world of 8 billion. Our numbers are supported not by simplicity, but by intricacy. Agriculture feeds billions, but only through fertilizers made with fossil fuels and machinery built in distant factories. Cities sustain themselves not with local fields, but with endless streams of trucks, ships, and power lines. Hospitals can cure illnesses once thought fatal, but they depend on supply chains that stretch across continents, with medications, equipment, and energy all arriving just in time. Remove one link, and the whole network wobbles. Remove several, and collapse cascades faster than we can respond. It's interesting to think about carrying capacity, the term ecologists use to describe how many individuals a system can support. Before the industrial era, the Earth may have been able to sustain around 1 billion people through traditional farming, fishing, and hunting. Today, our population is more than 8 times that size, possible only through industrial processes that transform nitrogen into fertilizer and pump groundwater from ancient aquifers. Take away those inputs, and the sustainable number falls again. The difference between 8 billion and 1 billion is not just arithmetic. It's the difference between a world full of bustling cities and a world where survival becomes a local question again. Food illustrates this clearly. Pollinators are disappearing, soils are degrading, and fisheries are under stress. Each of those threads was part of earlier discussions, But here they join into a single question. How fragile is our food web when billions depend on it moving smoothly? In some ways, we are running an experiment no previous civilization attempted. Can a species build its entire diet on systems that could unravel in less than a century? The answer may determine not whether humanity survives at all, but how many of us do. The same fragility shows up in energy. Our cities depend on electrical grids that can collapse in hours if demand outpaces supply. Data centers, water pumps, and hospitals all run on continuous current. Imagine a prolonged blackout in a major city, not just a few days, but weeks. Refrigeration fails, water stops running, sewage backs up, communications fall silent. The modern city, which feels like a fortress of stability, becomes a trap with glass walls. Migration is another piece of the human bottleneck. As temperatures rise, some parts of the world will become literally uninhabitable, not just unpleasant. Wet bulb temperatures, where heat and humidity combine so that the human body can no longer cool itself, are already being measured in regions of South Asia and the Middle East. By mid-century, projections suggest that billions could be living in zones where summer heat is incompatible with survival outdoors. Add sea level rise that submerges coastal cities, and we are looking at mass movements of people on a scale history has never witnessed. One recent estimate suggests over 1 billion climate refugees by 2050. It's worth asking, how does a global civilization, already stressed by political and economic divides, absorb such a movement without tearing apart? And then there is disease. For most of history, humans lived close to the edge of epidemics. Modern medicine has given us a cushion, but it is thinner than it seems. Antibiotic resistance is spreading, threatening to return us to an era where a simple cut can become fatal. Zoonotic diseases, those that jump from animals to humans, are increasing as we press deeper into wild habitats. COVID-19 was a reminder, not an exception. Add thawing permafrost that releases pathogens preserved for millennia, and we begin to see disease not just as an event, but as a recurring companion of a destabilized world. All of these threads, the food system, energy, migration, disease, come together in one larger idea, the complexity trap. The very interconnection that allowed us to build a world of 8 billion is the same thing that leaves us vulnerable. Simplicity resists collapse because it has fewer moving parts. Complexity thrives under stability, but fails catastrophically when stability disappears. We have built our lives on complexity, and we rarely ask what happens if that scaffolding shakes. It leads to a sobering reflection. In past extinctions, survival favoured adaptability. Small generalist species often made it through while specialists vanished. In our case, adaptability may not be about physiology but about culture and knowledge. Who remembers how to grow food without fertilizers, or build shelters without concrete and steel, or heal wounds without antibiotics? These are not skills most of us carry anymore. We have outsourced survival to systems larger than ourselves, and in doing so, we may have made our species less resilient than it appears. If the human story now hangs in a balance, it is not simply because of external forces, it is also because of how we respond to them, and what kinds of societies we become under pressure. History gives us glimpses of this too. When Rome fell, cities emptied, and knowledge became fragmented, but small communities adapted, preserving what they could in monasteries and oral traditions. When plagues swept across Europe in the 14th century, death reshaped economies and power structures as much as it changed families. What survived was not always the strongest army or the richest merchant house, but the cultures that found ways to adapt socially as well as materially. That lesson matters for us because resilience may come less from bunkers and walls than from relationships. There is a growing fascination among the wealthy with survival compounds, fortified estates in New Zealand, luxury shelters stocked with supplies, or even visions of colonies on Mars. These strategies imagine survival as separation, insulating a few against the collapse of the many. But history suggests that insulation rarely works for long. Resources dwindle, communities fracture, and isolation magnifies weakness. The survivors who endure in hard times are often those who lean on networks of trust and cooperation, not those who retreat behind locked gates. It is worth noticing that communities who never fully entered the modern industrial system may hold unexpected advantages. Indigenous peoples who still know how to forage, hunt, and steward land carry traditions that evolve to endure cycles of scarcity and abundance. Amish and Mennonite groups who live with little reliance on fossil fuels or global supply chains may be better prepared for a world where those links fail. Their way of life, often dismissed as outdated, may turn out to be a rehearsal for resilience. At the same time, it is not only the humble who adapt. Power often concentrates in times of collapse. Organised crime can seize resources, military bases may become survival enclaves, strong leaders rise in the vacuum of weakened institutions. This raises unsettling questions about what forms of governance take hold when democracy and trust erode under stress. Will survival be guided by cooperation or by coercion? Will new hierarchies harden quickly, deciding who eats and who does not? These are not just hypothetical musings. Already we see the early indicators: polarization, distrust in institutions, the spread of authoritarian tendencies. The bottleneck is not just ecological but political. Then there is the matter of numbers. Biologists sometimes talk about a minimum viable population, the smallest number of individuals needed to avoid inbreeding and retain genetic diversity. For many animals, that threshold lies somewhere between a few hundred and a few thousand. If humanity faced a collapse that reduced billions to scattered survivors, would our diversity be enough to carry us forward? Technically, yes. The Toba event showed we have survived with far less, but survival at that scale would be a far cry from the 8 billion person civilization we know. It would mean bottlenecks not just of genetics, but of knowledge, of culture, of possibility. Knowledge itself may be one of our most fragile inheritances. In a world where most information lives on servers and cloud storage, what happens if the power grid flickers out for years? Books may outlast batteries, but entire generations now learn through digital tools. A child who can stream any documentary on a phone may never learn to read a printed map. If those skills vanish in a single generation, they may not return. Think of how long it took humans to rediscover the engineering techniques of Rome's concrete, or the astronomical knowledge once preserved in ancient libraries. Each collapse erases not only people, but the scaffolding of memory. That brings us back to the essence of the bottleneck. It is not simply about how many survive, but about what survives with them. Will small groups carry forward seeds, languages, and stories? Will they preserve ways of farming and medicine that can rebuild a foundation? Or will they live in fragments, stripped of connection to the complexity that once seemed permanent? The danger is not just losing lives, but losing continuity, the thread that ties one age to the next. There is a haunting symmetry here. The Earth has seen bottlenecks before. After the Great Dying, life itself narrowed to a handful of hardy species in oxygen-starved seas. From those few, whole new ecosystems eventually blossomed. After the asteroid struck at the end of the Cretaceous, mammals that had been small and overlooked began radiating into every available niche. The story of Earth is not one of endings, but of thresholds, bottlenecks that prune and reshape the possibilities of life. The question facing us is whether our species passes through this narrowing intact enough to flourish on the other side, or whether we become just another thin line in the fossil record. What makes our bottleneck distinct is awareness. Trilobites did not know the seas were acidifying around them. The great reptiles of the Triassic did not track carbon dioxide levels, but we do. We measure the heat rising in the atmosphere, the acidity in the oceans, the decline in the soil. We know what's coming in ways no species has ever known before. The mystery is not whether collapse is possible, but what we will do with the knowledge that collapse is possible. Does awareness change fate, or only sharpen our understanding of it? It is a heavy thought, but it is also a curious one. Awareness cuts both ways. It can paralyze, leaving us scrolling headlines without action, but it can also seed resilience, prompting us to build communities of memory and practice before the scaffolding falls away. Perhaps survival, in the truest sense, will belong not to the richest or the strongest, but to those who can hold on to connection. Connection to land, to knowledge, to one another. As the thought comes into focus, the image of a human bottleneck is not just about numbers. It is about narrowing options, about watching the vast possibilities of a global civilization contract into a tight passage where only certain forms of life, culture, and memory can pass through. And like every threshold in history, it carries both danger and opportunity. On the far side may lie decline, but also renewal. What remains uncertain is what pieces of our present will slip through with us, and which will be left behind, fossils of a world that once seemed too large to fail. Chernobyl offers an unexpected glimpse into a world without us. When the power plant melted down in 1986, it forced humans to withdraw from the surrounding region. What remains is a landscape steeped in radiation, an invisible danger that should make it uninhabitable for life. Yet in the decades since, the area has become one of the richest wildlife refuges in Europe. Wolves roam freely, populations 7 times higher than in surrounding regions. Lynx, bears, bison, and eagles thrive in the silence left behind. The very radiation that makes it perilous for people has done little to halt the patient return of forests and animals. It is a sobering reminder. The Earth does not need us. We are the ones who need the Earth. This pattern has played out before. When humans abandon a place, even for a short while, nature reclaims it astonishingly fast. Roads crack as grass and weeds find footholds. Buildings grow damp and collapse under the weight of moss and trees. Within 10 years, neighbourhoods can look unrecognisable. Within a century, most structures return to rubble. 500 years after our disappearance, entire forests could reclaim land we paved over, and the only evidence of our presence would be scattered ruins and the faint signatures of our pollutants locked in sediments. Stretch that timeline further, and the traces become even fainter. After 1,000 years, carbon dioxide levels might finally begin to decline towards something closer to pre-industrial norms. After 10,000 years, most of what we built would be erased by wind, rain, and tectonic motion. 1,000,000 years from now, the world would hold entirely new lineages of species that evolved to fill the spaces we left behind. Life, as always, would continue, not as a museum of what we once knew, but as a new experiment written across oceans and forests. It is worth asking who or what might inherit this Earth. Some candidates are familiar. Rats, crows, and cockroaches have followed us everywhere, thriving in our shadows. Their adaptability might carry them forward into whatever environments remain. Cephalopods, octopuses, squids, cuttlefish already demonstrate startling intelligence without a backbone, and in a world without human dominance, their evolutionary story might continue towards stranger forms of cognition. Fungi, which already orchestrate the cycling of nutrients and communicate through vast underground networks, could rise into an even more commanding role. Extremophiles, microbes that thrive in boiling springs or deep ice, remind us that life is at home in conditions we consider lethal. And if machines ever learn to replicate themselves and draw energy independently, perhaps even artificial systems would linger, carrying forward a reflection of our ingenuity long after the hands that built them are gone. The fossil record shows that recovery is always possible, but never a return. After the Great Dying, it took 10 million years for ecosystems to regain something like their previous complexity. After the asteroid at the end of the Cretaceous, mammals, once small and marginal, radiated into every ecological niche. Each extinction event closed some doors forever, while opening others we could never have predicted. Innovation often follows collapse, though the forms it takes are unimaginable to those living at the edge of the old world. Even in the smallest realms, this creativity is at work. Bacteria are already evolving to metabolize plastics, turning our waste into a resource. New metabolic pathways emerge under pressure, reshaping the basic chemistry of ecosystems. In the oceans, as reefs bleach and die, new assemblages of organisms experiment with different ways of building habitats. Jellyfish blooms may be temporary rulers, but eventually other engineers, perhaps sponges, perhaps something entirely new, will carve out niches in the changing seas. In the deep ocean, chemosynthetic ecosystems around hydrothermal vents may expand, colonizing regions once too hostile. The collapse of one order is always the seedbed of another. Geologists sometimes speak of the Anthropocene layer, a future stratum in Earth's rocks that will carry our fingerprints. It will not be marked by our monuments or our cities, which will crumble away, but by subtler signatures. A plastic horizon embedded in sediments, radioactive isotopes scattered by nuclear tests, the sudden appearance of chicken bones, billions upon billions of them, fossilized as evidence of industrial farming. To a geologist 10 million years from now, these may look like the markers of a brief and peculiar age, a spike of human activity that came and went quickly compared to the eons before and after, And yet, even as we imagine the vanishing of so much, there will be seeds of recovery. Literally in the case of seed banks and gene vaults, which may survive long after their curators are gone. Zoos and captive breeding programs could leave genetic echoes that rewild themselves if given the chance. Invasive species, often blamed for disrupting ecosystems, might also play a role in knitting together new ones. Evolution, pressured by chaos, accelerates. The planet will not pause to mourn what is lost, it will improvise. Seen this way, the end of our dominance is not the end of life. It is only the end of life as we know it. Earth has endured asteroid strikes, ice ages, and atmospheres filled with poison. Through each, life has persisted, reshaped, and continued. What we risk losing is not the planet, but our place within its unfolding story. And that thought alone is worth sitting with. The idea that the Earth will go on writing chapters, whether we are in them or not. If we step back and look at Earth as a patient, the pattern becomes clearer. The vital signs may falter, the pulse may grow faint, but recovery is part of the body's nature. The question is never whether life will continue, but in what form. And what fades most quickly is not the living world itself, but the traces of any one species' dominance. We often think of ourselves as permanent fixtures in the story of the planet, yet the timeline suggests otherwise. Imagine an abandoned city 1,000 years from now. Towers collapsed, streets buried, rivers cutting new paths through concrete. Moss and ivy cover what was once glass and steel. Deer wander through subway tunnels. Owls nest where office windows once lit the night. From space, the outlines of human civilization would already be fading into the green of forests and the brown of deserts. In some ways, the most lasting monuments might be the ones we never intended: chemical signatures, fragments of plastic, the faint dusting of radioactive isotopes. To future life forms, these would be the fossils of us. What makes this reset intriguing is that it rarely restores what came before. Life does not rewind, it reconfigures. After the Permian collapse, the planet was a wasteland for millions of years, yet out of that emptiness arose new forests, new reefs, and eventually creatures that had never existed before. The age of reptiles gave way to the age of mammals, not because mammals were destined to rise, but because they were adaptable in the ruins left behind. Extinction prunes, but it also clears space for what could not thrive in crowded conditions. This is not to say recovery is gentle. For long stretches, Earth may look diminished. Imagine seas dominated by gelatinous forms, landscapes ruled by opportunistic species we now consider pests. It might take tens of millions of years before biodiversity regains the richness we know today. Yet patience is one of Earth's defining qualities. Evolution needs only time and pressure, and both are in endless supply. The thought can be unsettling, that we might become only a thin layer in the fossil record, our skyscrapers reduced to shadows, our voices silenced, while new life quietly experiments in the niches we once filled. But it can also be strangely liberating. If Earth does not need us, then perhaps our challenge is not to save the planet in some absolute sense, but to decide what kind of place we want to occupy while we're here. Are we caretakers, participants, or simply another brief flare of activity that burns bright and fades quickly? Consider how often myths and stories already carry echoes of this idea. Flood narratives from Mesopotamia to the Americas describe waters sweeping away old worlds, leaving survivors to begin again. Hindu cosmology imagines cycles of creation and destruction, universes dissolving and reforming in endless rhythm. Even in modern science fiction, the theme repeats. Civilizations rise, collapse, and something new takes their place. Perhaps we intuitively recognize that resets are woven into the fabric of time. The mystery is not whether they happen, but what shape they take. Seeds of renewal are often unexpected. Invasive plants spreading in disturbed landscapes may become the backbone of future ecosystems. Animals adapting to urban environments may carry forward traits that serve them well in wilder settings. Even our ruins, toxic as they may be, can create novel niches. Concrete crumbles into limestone-like habitats for mosses and lichens. Old mines fill with water and become reservoirs for fish and amphibians. Landfills layered with waste may one day be compressed into geological strata, rich in new minerals for species yet unborn. It is also worth reflecting on how quickly balance can return in places we step aside. Marine reserves often see fish populations rebound dramatically within a decade once fishing ceases. Forests regrow where logging stops, often faster than expected. Even degraded soils can recover if given rest. The speed with which life reclaims space is a reminder that recovery does not always wait millions of years. Sometimes it begins almost immediately, as if the world has been holding its breath. All of this points to a humbling truth. Life is far more resilient than we are. Our cities and cultures may feel immense, but in geological time they are fragile constructions. Strip away the scaffolding, and the Earth continues almost indifferently. The lesson is not despair, but perspective. We can either be part of the long continuity of renewal, or we can step aside and watch as life rewrites itself without us. What emerges from that thought is not a story of endings, but of transitions. Extinctions are thresholds, not full stops. They are moments when the page turns, when the cast changes, and the stage is rearranged. We may grieve what is lost, and rightly so, but the deeper mystery is always what comes after. And what comes after us will not be emptiness. It will be something strange, unfamiliar, and alive in its own way. So when people speak of saving the planet, perhaps the phrase is slightly misleading. The planet will save itself, as it always has, in rhythms longer than our comprehension. What hangs in the balance is whether our species and the worlds we cherish will be part of that next chapter, or whether we will be remembered only in sediments and isotopes, a brief flare preserved in stone. For many, imagining collapse means conjuring movie-like visions, stockpiled shelters, scattered survivors, and cities breaking down around them. But real survival rarely looks like the movies. It is quieter, stranger, and often rooted in communities and places that most of us overlook. The last time humanity nearly disappeared, 74,000 years ago after the Toba eruption, it was not the strongest or the richest who pulled through. It was small bands of hunter-gatherers armed with stone tools and fire. They endured by moving lightly across the land, reading rivers and seasons, sharing knowledge face to face. From just a few thousand individuals, all of us descend. That lesson is worth remembering. Survival is not always about technology or wealth, but about adaptability and connection. Geography matters too. Some places simply offer better odds. Islands with low populations and stable climates, New Zealand, Iceland, Tasmania, could become refugees if global systems falter. They are far from the densest centres of conflict, buffered by oceans, and in some cases powered by renewable energy like geothermal or hydropower. Patagonia, with its sparse population and abundant fresh water, may serve a similar role at the southern edge of the Americas. In the far north, regions of Canada and Alaska still hold vast tracts of forest, fresh water, and low population density, resources that could sustain people, even if the global grid goes dark. But geography alone is not destiny. Survival also follows culture. Indigenous communities that still maintain traditional knowledge of plants, animals, and landscapes may hold keys to living through disruption. Many already know how to grow food without industrial fertilizer, how to navigate without GPS, how to heal using local remedies. In a future where supply chains vanish, these skills could matter more than digital literacy or financial expertise. The same could be said of Amish and Mennonite groups, who live with little reliance on fossil fuels and have proven resilient through centuries of change. Their separation from the technological mainstream, often seen as an anachronism, might turn out to be foresight. There is also the uncomfortable possibility that some of the best prepared groups are those we would not expect to admire. Preppers, often dismissed as eccentric, may indeed have an advantage if they have cultivated self-sufficiency rather than just stockpiles. Criminal organisations, skilled at controlling territory and resources through networks of loyalty and coercion, may also find ways to thrive in fractured landscapes. Military bases, with their supplies, discipline and infrastructure, could become islands of order in seas of chaos. Survival, after all, is not about ideals. It is about persistence. One of the great ironies is that cities, the crowning achievement of human complexity, may become the least survivable places. Urban centres depend on electricity, trucking and steady imports of food and water. Without those, the density that once made them vibrant becomes dangerous. Suburbs, which combine dependency with sprawl, may fare no better. Rural communities, by contrast, still know how to hunt, fish, farm, or fix machinery, though they too may become targets for raiders if law and order break down. In uncertain times, mobility may once again become a survival trait. Nomadism, long abandoned by most of the world, has historically proven one of the most resilient human strategies. Technology, curiously, becomes both a blessing and a trap. High-tech systems give us medicine, power, and comfort, but they are fragile, lose the grid, and much of our accumulated knowledge disappears in a generation. Digital archives require electricity, servers decay when left untended. Without books or teachers to carry them forward, whole disciplines could vanish. Low-tech knowledge, how to build a fire, mend a roof, purify water, may outlast advanced sciences if memory falters. The paradox is that the very complexity we celebrate could evaporate faster than the simplest skills of survival. Social structures are just as important as tools. In moments of scarcity, democracy often falters, giving way to strongman rule or tribal governance. Small groups cohere quickly under pressure, but larger institutions splinter. History shows that women often have higher survival rates than men, perhaps because of social networks and adaptive roles. Children, though vulnerable, can also be a resource, new hands, new energy, if communities remain strong enough to protect them. The bottleneck of survival is not just ecological or technological, it is social. Trust becomes currency, and isolation becomes a weakness. The groups most likely to endure are not necessarily the wealthiest or most armed, but those able to knit themselves into communities where knowledge, labour and care are shared. That truth has been repeated in collapses from Rome to the Mayans, from the ancestral Puebloans to smaller, local declines. Civilizations vanish, but people in communities endure. And so survival begins to look less like bunkers and more like villages, less like fortresses and more like networks of memory. The question becomes not simply who survives, but what survives with them. What stories, what seeds, what fragments of culture pass through the narrowing corridor of time. When we think about survival in the long term, numbers begin to matter. Biologists studying endangered animals often ask how many individuals are needed to sustain a population. The answer usually falls somewhere between 500 and 5,000. Fewer than that, and inbreeding depression weakens resilience. Too little genetic variation leaves species vulnerable to disease. Humanity, if reduced to scattered enclaves, would face the same biological mathematics. Technically, we could rebound from small numbers. We already did once after the Toba eruption. But the quality of that survival would be very different from the expansive global civilization we know today. It is not only genes that risk being lost in such a bottleneck, but knowledge. Imagine if entire regions go dark for generations. What remains is what people can carry in memory, in stories, or in books. Oral tradition, once the backbone of human continuity, may again become vital. A myth may not preserve the full detail of a farming technique or a medical treatment, but it can carry the shape of wisdom across centuries until someone rediscovers its meaning. In that sense, survival is not only about bodies moving through time, but about ideas finding vessels. This makes us wonder what knowledge would be prioritized if collapse pressed us to choose. Which books would you rescue from a burning library? What skills would you teach your children if you knew they might be among the last to carry them? Historians sometimes call this the Leonardo da Vinci problem. A single person with rare knowledge can alter the course of a generation, but only if that knowledge is preserved and transmitted. In a fractured world, those figures may not be artists or scientists in great institutions, but elders and storytellers who hold fragments of memory others forgot to keep. The paradox of survival is that the very traits we celebrate today may not matter much in a world remade by collapse. Digital fluency, financial expertise, or academic specialization could fade into irrelevance if grids fail and universities close. Meanwhile, forgotten skills, mending clothes, storing food, reading the weather, could become the currency of life. This inversion is unsettling, but it is also familiar. Civilizations that collapsed in the past left behind ruins filled with broken statues and eroded texts, while the people who carried on were farmers, herders, healers, and builders. And yet, even with all of this reflection, we cannot ignore human ingenuity. there is always the possibility that scattered survivors preserve enough knowledge to leapfrog back into complexity faster than any species before us. If even a handful of libraries, archives, or digital backups remain accessible, they might shorten the dark ages of recovery. A village that remembers how to smelt iron or harness wind could rebuild foundations in centuries rather than millennia. The line between collapse and renewal is not always clean. It depends on what is carried through. It is also worth remembering that survival is not necessarily scarcity forever. The Earth after us may look empty at first, but over generations, ecosystems will reorganize, forests will regrow, rivers will clear, and new balances will take shape. For the survivors, that means a chance to rebuild in a world still fertile, though different. Perhaps the greater challenge will not be surviving the bottleneck itself, but resisting the temptation to repeat the same patterns that brought collapse in the first place. What makes this whole thought exercise haunting is how personal it is. Most of us do not imagine ourselves in the role of a distant descendant tending crops in the ruins of old cities. We picture ourselves here and now in the modern world, but the idea that survival might belong to people far removed from our present comforts invites humility. It suggests that what endures of us may not be our technology or our monuments, but our adaptability, our culture, and our memory. If we carry anything forward, perhaps it should be the recognition that survival is not about hoarding or hiding, but about connection. Communities that endure are not built on walls alone, but on shared labour, trust, and the stubborn decision to keep telling stories even when the night is long. That may be the real survival strategy. Not the bunker, not the arsenal, but the campfire. A circle of people keeping the embers alive until dawn. We often hear numbers tossed around as if they carry certainty. 6 years to peak emissions, 20 years before ecosystems collapse, 50 years before feedback loops become unstoppable. These figures can feel heavy, almost like countdown clocks. But it's worth remembering that the Earth doesn't measure time the way we do. What matters is not a precise date, but the direction of change, and whether we have the will to alter it. Right now, we stand at a peculiar threshold. On one side are possibilities we already know: burning fuels, clearing forests, consuming faster than the world can regenerate. On the other side are paths that would look different: restoring land instead of exhausting it, protecting oceans instead of emptying them, designing economies that cycle resources instead of discarding them. None of this is fantasy. Rewilding projects have already shown how quickly species return when given space. Regenerative farming has proven that soil can heal and store carbon again. In protected marine sanctuaries, fish populations rebound within a decade. Even energy is shifting, with wind and solar now cheaper than fossil fuels in many regions. These are glimpses of futures that are not yet lost. The difficulty lies in scale. Healing a valley or a reef is one thing. Healing a planet of 8 billion people is another. The transition would require reshaping how nearly every human society operates, and at a speed no civilization has ever managed before. Political systems tend to move slowly. Economies resist change. Corporations cling to profit models built on extraction. And yet, the physics of the atmosphere do not wait for parliaments or markets. Greenhouse gases accumulate whether we act or not. The clock may not tick the way headlines suggest, but momentum is real. Every year of delay locks in deeper warming, makes adaptation harder, and narrows the corridor of choices left to us. Scientists speak of tipping points. Thresholds that once crossed are difficult, perhaps impossible to reverse. The Amazon rainforest could shift from forest to savanna if deforestation passes a quarter of its area. Antarctic ice sheets may be committed to collapse if warming exceeds 2 degrees. Permafrost thaw could release so much carbon that it drives further warming no matter what humans do. Coral reefs may largely vanish if temperatures rise beyond 1.5 degrees, and we're already brushing against that limit. These are not abstract lines, they are cliffs, and each step toward them makes the ground more unstable. Faced with this, some argue for emergency measures: spraying reflective particles into the stratosphere to dim the sun, or building machines to pull carbon from the air on unimaginable scales. Geoengineering, carbon capture, massive nuclear build-outs. Each proposal comes with risks as great as the problems they aim to solve. Intervening in Earth's systems may ease symptoms, but it may also create new imbalances. The danger is trading one unknown for another. Others look to social solutions, rationing resources, embracing degrowth, reducing consumption, stabilizing or even reducing global population. These, too, are fraught with difficulty. Human nature resists limits. Our cultures are built on growth, on the idea that more is always better. Asking billions to embrace less is not just an economic question, but a psychological and cultural one. It cuts against centuries of momentum. So we return to the haunting question, why don't we act when the stakes are so clear? Perhaps it is the tragedy of the commons, where shared resources are overused because no one feels ownership. Perhaps it is the way humans discount the future, valuing the present over generations yet unborn. Perhaps it is the sunk cost of a civilization that has built itself on fossil fuels, making it hard to imagine another way. Or perhaps it is simply that we are reactive creatures, better at responding to disasters than preventing them. And yet within this tangle there are signs of change. Youth movements demanding climate action, local communities restoring wetlands or planting forests, cities investing in renewable grids, even when national governments stall, technology racing forward in surprising leaps, nature itself offering resilience, bouncing back when given even a sliver of space. The path may be narrow, but it is not invisible. It runs alongside despair, a reminder that possibility remains even when probability feels thin. The honest timeline is not easy to hear. By the middle of this century, food systems will likely be under strain, and migration will reshape the map of nations. By the end of the century, the human population may decline to a new equilibrium, not through choice but through pressure. The question is not whether change is coming, but how it unfolds, managed descent or chaotic collapse. The future could hold a world where billions endure hardship, or one where smaller numbers rebuild with more balance. This is not the kind of hope that promises a clean escape. It is the kind that acknowledges loss while still seeking to shape what remains. Perhaps we cannot avoid the sixth extinction, but we can still influence its depth and duration. We can choose whether half the world's species vanish, or nearly all. We can choose whether billions of people survive, or only millions. These are not small choices. They are the difference between a planet scarred and a planet emptied. It may be too late for the world we grew up in, the stable seasons, the abundant seas, the sense that tomorrow would resemble today. That world is already fading. But it is not too late to shape what replaces it. We are not the first species to face extinction pressures, but we are the first to see them coming and to debate our role in them. That awareness is itself a strange kind of power. Whether we use it is another matter. When you look across history, civilizations rarely chose to collapse. They grew until the edges frayed, until fields could no longer yield enough grain, until rivers shifted course, or invaders found weakness. The pattern is almost always the same. Decline comes not from a single blow, but from the slow accumulation of pressures that no one quite knew how to stop. And yet, within those endings, people always found ways to carry something forward. Language, tools, stories, fragments of memory that became the seed of what came after. That is perhaps the most honest way to think about our moment. It is not a choice between apocalypse and salvation, but between degrees of loss, between how much can still be saved and how much must inevitably change. We cannot preserve everything, but we can decide whether the next few centuries are marked by chaos or by care. The scale is daunting, but the essence is familiar. It is the same decision every generation faces, whether in droughts, wars, or pandemics, how to pass on as much as possible to those who come next. And here is the strange comfort. Nature is patient in ways we are not. Give a forest a few decades of rest and it grows back. Leave a reef unharvested, and fish populations rebound. Soil, if treated gently, begins to heal. The planet does not ask for miracles, only for space and time. The real question is whether we are willing to give those gifts, or whether we are too bound to the momentum of the present to loosen our grip. The seeds of hope are scattered more widely than we sometimes notice. Youth movements pushing for climate justice, communities experimenting with new forms of agriculture, nations slowly building renewable grids, all are fragments of a larger possibility. Technology too may hold surprises, advancing faster than our imaginations keep up. And through it all, nature keeps reminding us of its resilience. reclaiming even the most damaged spaces when given a chance. Still, we should not mistake resilience for invulnerability. Life will continue, but whether it continues in a form that sustains billions of people, with cultures and histories intact, is less certain. The choice before us is not whether the Earth lives or dies, but whether we carry forward into the next chapter as authors or as fossils. That may sound stark, but it is also clarifying. It places responsibility where it belongs, not in abstract forces but in our collective decisions. So are we too late? For the familiar world, yes. The stable climate, the abundant wildlife, the sense that the future would always look like the past, those are already gone. But for what comes next, we are not too late. We still have influence, not over whether change happens, but over how deep and how harsh that change will be. Between losing half of the world's species or nearly all, between billions surviving or only a fraction, between a managed descent and a chaotic collapse. It is unsettling to live in a moment where the page is turning, where the story we inherited is ending, and the next one is not yet written. But perhaps that is also what makes this moment meaningful. To recognise that we are both the cause and the witness of such change is heavy, but it is also rare. Out of all the species that ever lived, only ours has had the chance to reflect on its place in deep time, to wonder what future lineages will make of the traces we leave. Maybe that is the gift buried in the weight of this era. Awareness, the ability to see patterns in the fossil record and to notice their echoes in our present. The ability to know that tipping points are real, that feedbacks are accelerating, and that choices still remain. The awareness that even in loss, possibility endures. The story of the next mass extinction is already being written. The question is not whether it happens, but what shape it takes, and what we decide to send forward through the narrowing gate of time. Maybe it will be seeds, maybe stories, maybe only fossils, but whatever remains will stand as a record of us, not just of what we built, but of what we chose to protect. Because in the end, we are the only species in Earth's history to see the storm coming, to know the stakes, and to understand the cost of silence. And that knowledge alone is a kind of power. The only mystery left is whether we use it, or whether the future writes our name into stone as just another layer in the long memory of the Earth. Thank you for watching,